These are both written as reductions. One is going to have to be turned around to be an oxidation. When you turn one of them around, when you add the two potentials together, it's got to be a positive number. If I turn this one around, it's going to make it negative 0.34, but negative 0.34 added to 0 is going to be a negative value for the cell potential. Can't have it. It's not going to make any electron flow. So it's got to have the hydrogen side turned around. So it's going to look like this. Copper with a positive 2 plus, again, we're turning that thing around, so it's hydrogen gas yields copper metal plus that thing turned around 2 hydrogen ions. And this copper was aqueous. That's our balanced chemical equation. What is the N value in this case? Yeah, we didn't have to do any balancing on this because this was taking in 2 electrons, that one gives off 2 electrons, so that was nice. If we didn't have the same number of electrons, we'd have to balance that next. Yes?
Shouldn't it be the other way around, like 2H plus gives H2, because that is the reduction equation, and right now there's like 2 oxidations happening?
No, the copper is reducing from positive 2 down to 0.
Gaining electron.
Oh.
And the hydrogen is going from 0 up to positive 1. So we've got one going down and one going up. Okay? So the cell potential, the standard cell potential, is going to be 0.34 plus 0 is 0.34. Yes? Oh, we're not there yet. We'll do the Q now. It says this hydrogen electrode was a standard hydrogen electrode. That meant that this was 1 molarity, and this is 1 atmosphere. It's a standard hydrogen electrode. So that is brought down here. I guess I should have put 1.00, but that's what it is. The copper over here is a solid. We're not going to have any number under. And then the copper ion has its concentration right here. It's 2.5 times 10 to the negative 4. So we can now find Q. What's kind of weird about this is I think this is the first example that we've ever seen where you have a reaction that includes an aqueous thing and a gas. Well, how do you do Q? Q is the products over the reactants, but usually we have everything in molarity. Well, if your gas is in if your gas pressure is given in atmospheres, just count it like as if it's aqueous. Just put 1 for its value. So we're trying to find the cell potential. Epsilon equals epsilon naught minus 0.0591 over n log of Q. So the standard cell potential is right there. It's 0.34 minus 0.0591 over 2, and it's 2 again in this case, times the log, and it's going to look like this. The right side is 1 molarity. I'm not going to put the m in there. Just put the number. And it does get squared. When it's a 1, it's not a big deal. But don't forget, if you have a coefficient, you have to raise it to that power. Over the 2.5 times 10 to the negative 4th, and then over 1. That's how we use the Nernst equation to find the new cell potential. And now this has been going, well, I guess we're very much product heavy on this thing. So this should lower the voltage, and does it? Is the voltage lower than standard? Yeah, because the reaction is product heavy. We have a very low concentration of one of the reactants. What is the new cell potential? 0.23. Yeah, it's 0.23 volts. Okay, is there anything that's fuzzy about this?
Yeah.
Uh-huh.
Why are we using atmosphere?
I know that's kind of weird that we would put both molarity and atmospheres in there together, but especially because it's at standard. I mean, when your standard value is 1, It's almost like a proportional change. If it went up to 2, that would mean that the pressure doubles, it goes to 1.5, pressure went up by 1.5. So, yeah, as long as it's in atmospheres, it works. You can include atmospheres as if it's molarity. Kind of weird like that, I know, but it's the way that we do Q. And we won't see too many examples like that. Usually it's all aqueous or all gas, not some of each. Anything else about this one? Okay.